we have reactions in which we can have the forward and the reverse occur. So here, just a second. And so for these types of reactions, we'll usually show two arrows, one arrow going forward, one arrow going reverse. Initially, when you start the reaction, we only have forward reaction occurring. The forward reaction, if we were to plot it out, you can see if we look at the amount of copper 2 and tin 2, we start off at the same amount here. And so let's have the copper 2 maybe as a blue line here at 0.100. And then the tin is this kind of magenta line here at 0.100. And as the reaction progresses, we're going to consume twice as much copper 2 as tin 2. And so the copper 2 is going to decrease over time. And we don't know, is this a linear decrease or what is it? You know, curve decrease? But we'd have to measure it. And so I'm just going to show it as kind of linear here. But the tin is going to be consumed at half the rate as the copper. So we end up with something like this. But the thing is, we don't completely consume all the limiting reagent. We only consume 64% of the limiting reagent, and then what happens here is nothing. It just stays flat. And the same thing with the tin too. It is going to stay flat here. So initially, there's just going to be forward reaction. The forward reaction is going to consume reactants here until we hit this. Once we hit this, this is the end of the reaction here. So it doesn't matter how long we wait for this reaction to complete, it's not going to complete. And so this is it. This end is what we call the equilibrium state. Equilibrium means there's no change here. And there's going to be no change in the amounts here. Initially, we start off with 0 of the copper plus and 0 of the tin 4. And so let's try some different colors here. So green. Actually, I'll just make it blue if I can. So the copper plus is going to increase to 0.64. So this is the product. I'll just make the line a little different until we hit this equilibrium phase. And then once we hit the equilibrium phase, this is not to scale. I should probably look more carefully at it. And then the tin 4, also the tin 4 is going to be produced at half the rate or half the amount. And so it would be something like this. So let me see if I have this to scale. And so we have 36 for the copper 2 plus. So this is going to be 0.036. Or just 36. It's for the moles. And then for the tin 2, we drop down to 668. And so this will be 0.068. Okay, these are the reactants here at the end. Now for the products, we're going to end up at 0.64 for the copper. And so, sorry, I made this wrong here. Because if it's 0.64, it's got to be below this magenta line here. So let me try it again. Here. Just redraw this. They're almost the same. I mean, 68 versus 64. It's very close. So this will be 0.064 as far as the product goes. And then the tin 4 is going to be at 32. So the tin I really screwed up. That's going to be below this blue line here. So I need to correct that here again. almost the same. 32 versus 36 here. This is the product. Okay, so let me make it a little bit bolder here so it stands out more. And the same. Here for the product. The product, I'm going to make this squiggly line. The reactants just made the solid line. Maybe I should do a different color for that. Here. I have plenty of colors, but I didn't. And so initially what we're going to have is we're going to have the forward reaction occur. When the forward reaction occurs and we populate some of the product state, then the reverse reaction is going to occur because we can't stop these from colliding. As a copper plus collides with a tin 4, there's potential for reaction. So immediately when we form some of this product, the product can react and go backwards. And so the progression of the arrows would look something like this. If I'm looking at the rates, looking at the rates, initially it's all forward reaction here. And then as the reaction progresses, I'm going to get mostly forward reaction. Actually, I need to narrow this down. Let's see if this. Mostly forward reaction, and then we're going to get a little bit of reverse reaction that takes place here. And so mostly forward reaction and a little bit of reverse. And the reverse reaction is going to continue to grow. As the concentration becomes higher and higher, the reverse grows. And then what happens is we get to the point where, we have the amounts of product here high enough such that the reverse reaction is going to equal the forward reaction. And then things stop changing. Things stop changing as in the amount stop changing. And so once we hit this state of dynamic equilibrium, then the concentration of product has reached this point where the collisions between the product species produces enough reaction to completely cancel out the forward. It doesn't really cancel it out. But that's one way of thinking about it because there's no more net change. So once we hit the state of equilibrium here, we get forward and reverse reaction occurring at the same rate, and that stays throughout the entire. So we could wait forever and nothing's going to change here as long as the temperature and other factors don't change, but it just stays stable, this ratio here. Now, it's a dynamic equilibrium. A dynamic equilibrium means that the individual reactions don't stop. You can't stop these from colliding. They're going to collide, but they're going to collide in both directions. So we're going to get forward and reverse. And so this is why we call it dynamic, and this is why we show the arrows. The reaction doesn't stop. It's occurring. It's just that the rates of the forward reaction and the rates of the reverse reaction are equal. Now, when we look at this, this comes out to 360, 680, 640, and 320. So it's pretty close. It kind of looks like a 50-50 kind of mix of this. But when we look at the tin itself, the tin has more here, less here. And the copper has less here, more here. So anyway, we're looking for patterns. And one of the patterns that we can see is from the graph. So oftentimes in science, when we're looking for patterns, we try to graph it and try to visualize it like this. And so this would be a visual representation of that. Do you see a pattern there? Yeah, it kind of looks like there's a pattern, It looks like the magenta here of the product and blue the reactant, and then blue of the product and then magenta. So it looks like the two blues are on the inside and the magentas on the outside. Do you see that pattern? Or there's another one here. When we look at the limiting reagent, one of the key things is in Chem 1A we had 100% reaction or 0% reaction. Here, how much percent reaction did we have? Well, we started off with 100, and we end up with 36, so that means we lost 64. So 64% reaction in this particular case. So that's another pattern that we might look for here. Okay. So we go to experiment 2, and in this case, we said which one's the limiting reagent. Now we're just going to look at the reverse, because the reverse reaction can occur, as we see. And these reactions are reversible reactions, not one-way reactions. In this reversible reaction, we just start off with products and go backwards here. So we start off with 100 and 100 here, and then just go ahead and let it run its course. And so over time, let's see what happens in this particular instance here. And so we're just going to graph it again and see. You can see from the graphs. So I have the copper starting at 0.100, and this is now the product copper here. So we'll just start it here. And then it's going to drop down to 64. So we're just going to only lose 32% of the copper. Oops. And so initially we're going to have the reverse reaction occur, and so the amount of product here is going to decrease as the reverse reaction occurs. And if it's linear or nonlinear, we need to measure that. I'm just guessing here because I only have the end data point here. I don't have the data over time. And so we lose a little bit, and then we stabilize at 64. Okay, when it hits the end or the equilibrium of this. And then there's no further change. Oops, that's the wrong color. Let's do blue. So again, this is the moles. And then let's go to tin 2. No, not tin 2, sorry. Tin 2 starts at 0. We've got to go to tin 4. Tin 4 starts at 0.100. So we'll have the tin 4 here. And the tin 4 started at 100 and ends at 84. So we didn't lose much. How much did we lose? We only lost 16%. Okay, and so we end up at 84 here. Okay, as the same thing happens here, as the reactant, reactants start off at 0 here. These are really the reactants. We just wrote the reaction backwards, which is fine. We're just going in the backwards direction. But as the products are being consumed, we're going to start forming more reactants. So we start off at 0 for the copper, and we're going to end up at 32. So I'm going to start off at 0 here for the copper, and we're going to end up at 32 once we hit equilibrium. And so that's going to be 0.032. And then for the tin, we start off at 0, and we end up at 16. Okay, now let's take a look at this pattern. It kind of looks, do you see that? It looks like there could be a pattern there. Do you see that? However, they're flipped. It looks like it's flipped because over here, let's see, you know, it kind of looks like a pattern because we go magenta blue, but this is magenta solid, blue squiggly. And then here's magenta squiggly and blue squiggly. And then down here is blue solid and the magenta squiggly. And then we go down here and it's blue solid, magenta solid. So maybe there's a pattern or maybe there's not, do you see? I'm trying to figure out if there's a pattern because, well, I mean, this is what scientists do day to day. You know, day to day they collect the data, right? And if they're studying a new system, they want to understand the system. They're going to look for patterns, trends. So that's what we're doing, looking for patterns and trends. Well, the more data we have, the more observations we have, the better. And so we'll take another one. But let's see if we could see some other stuff here. So if we look at the copper plus was the LR, the limiting reagent here. And if we look at the percent reaction, how much was the percent reaction of the limiting reagent going backwards? So we started off at 100 and we end up at what? $64. So what was the percent reaction? %32 reaction. We lost 32. So if we start off with 100, and you start off with 100 people, you lose 32 people. What percentage of the people did you lose? 32%. You can call that percent reaction because that's how much actually reacted. 64% is left over unreacted. This is something we do commonly. We are interested in percent reaction. Whereas before, what was it? Well, we had 64% reaction. Now we have 32%. So what we're going to do is we're going to go to experiment 3 and collect some more observations for this. So we'll take our copper 2+, which is a decent, what, oxidizer or reducer? Oxidizer, yeah. It's going to oxidize our tin. Tin 2 is actually a pretty good reducer. Tin 2 is used as a reducing agent for lots of reactions because it's a pretty good reducer, meaning it gains electrons easily or loses electrons easily. If somebody said tin 2 is a pretty good reducer, that means it gains electrons easily or loses electrons easily.
If it's a good reducer,
If it's a good reducer,
then it gives the...
yeah, it gives the electrons, it loses electrons easily. And if somebody said copper 2 is a decent oxidizer, that means it takes electrons. All right, and so in this next one, we know that this reaction is reversible. It can go both ways. And so we're going to start off with 0.100 molar, or not molar, 0.100 moles, sorry, of copper 2, 0.100 moles of tin 2, 0.100 moles of copper plus, and 0.100 moles of tin 4. There's going to be some change. We can figure out what that change is once we know what the final amounts are. And so let's take a look at the final amounts here. Actually, let me do the date. So the date is going to be 2/25. All right, so I'm going to take a look at the data for this. Just go back to the data. I don't need that anymore. Oh, I got signed out. We end up with 922, 961, 922, 961. Just copy this. Nine 961. For the products, we end up with 1078 and 1039. The first question I would have had is, which direction should this have gone? Should this gone forward or reverse? Would you have been able to predict it based on the observations so far? Looks like when we had a reaction 1, we started off with 0.100, 0.100 of the reactants and it went forward. There's nothing. In reaction 2, we started off with 0.100, 0.100 of the products, it went reverse. Now we have 0.100, 0.100 of everything. So will it go forward or will it go reverse? Are you able to predict it yet? No. I mean, unless we see some kind of pattern. That's a consistent pattern. But anyway, based on experimental fact, and this is what we're doing. We're just taking observations because that's what happens once we reach equilibrium. So let's take a look at the changes. Well, we must have lost some reactant here. So this is going to be minus, how much did we lose? Not much. We lost 0.0. What would that be? 0.0078. 0.0078.
Yeah.
So if I go 3 decimals over, I just lost 7.8% of my copper. And so I'm going to write that here. In other words, this had 7.8% reaction. This is copper again is our limiting reagent if we go forward, the forward direction. And we had 7.8% reaction. The tin is our excess reagent, so we don't really do percent reaction based on the tin. But how much tin did we lose? So this is
0.0039.
the tin only had 3.9%. It has to be half. It has to be half because of stoichiometry. Copper is a 2-to-1 stoichiometric ratio, so this is half of it, which is 3.9%. But again, when we do percent reactions, we usually look at just at the limiting reagent, not at everything, unless we're curious about the tin. And then over here, the copper, this is pretty easy because this is what we call a minus 2x. This is a minus x. And therefore, based on the stoichiometric, where do I get 2 and where do I get 1? That comes from the coefficients here. This is 2. I don't know what x is, but we figured it out. But we know it has to react in a 2-to-1 ratio. And the products are also going to form in stoichiometric quantities. That's going to be plus 2x. So if minus 2x is 0.0078, then plus 2x is just going to be plus 0.0078. Here. And so we increased it there. And then this is going to be plus x over here because of the, conservation of mass. Stoichiometry still works for these, even though the partial reaction, it's going to be plus 0.0039. All right, and so, looking at the numbers is kind of hard, because this had 7.8% reaction. This had 32% reaction reverse. This had 64% reaction forward. So can we make predictions based on percent reaction? Is the percent reaction always the same? Does it seem like it? No. And so percent reaction is not going to be reliable. How about the graph? Maybe we'll see a pattern in the graph. Sometimes it's hard to see. When you look at these numbers, do you see a pattern? When you look at the numbers? It's hard to see, huh? And so this is why people love graphs, because when you graph the data, sometimes you can see patterns that you wouldn't be able to see just in the raw numbers. And so in science, this is one of the first things that most people do is they graph it. They graph it to see, is there something there? And so now everything's starting off at 0.100, so we have here. So this copper just barely lost any. So once we hit equilibrium, it's at 0.0922. And then this tin 2, we lost even less, and so we're at 961. And then our copper 1, we started here at 0.100, and we gained a little bit, 1078. And then our tin 4, we gain a little bit less, 1039. I'll have to write that over here, 0.1039, since I didn't give myself enough room. So 1078, 1039. So let's look at the pattern in the graph. So we have blue, squiggly, magenta squiggly, magenta solid, blue solid. Is that the same pattern as before? Does it look like it? No. Does it look like the graph is going to be very effective in helping us predict reaction 4? So I'm going to do experiment 4 next. And what do you want to put in here for the initials? I'm going to do it like this. Let's make this one at 0.100. But now I'm going to do this like a stoichiometric. So this I'm going to make it at 0.050 moles. We need twice as much copper as tin. So now this is stoichiometric. If I leave this as stoichiometric, should it react completely? What do you think? Will it react completely? It doesn't react completely. This is still a two-way reaction. And then over here on the product, I'm going to make this one at 0 moles. And then over here for the tin, I'm going to make this 0.100 moles. And then there's going to be some kind of change, and then we're going to wait until the change stops and we hit the end of the reaction or equilibrium. All right. So why don't you take a little time and then tell me or predict for me what experiment 4 is going to yield. So look at this, and I want you to see if you can find a pattern to these numbers in the first 3 experiments, such that we can predict what's going to happen in the 4th experiment without having to actually measure it. You know, I don't have the experimental data for this one, but what we'd like to do is we'd like to predict what's going to happen. So this is what you do in science. Actually, not just like the physical sciences, but I was watching this TED Talk about a social scientist. Her name starts with a B. Forgot. Bridge something. Anyway, she was talking about like human behavior and what she did. She took lots of observations. She had studies involving lots and lots of people. And so she had a bunch of observations, and what she said was she threw, pages of observations on her floor, pulled up a chair, and just stared at the observations. Stared until the patterns came out. So you could try that. Just stare at this data until the patterns come out. Maybe you could visualize the pattern. Can you see the pattern? Do you see a pattern in there? Or is it just totally random? What do you think? Is there a pattern in there, or are things just completely random? So one of the things you can do is just stare at the data until some patterns come out. That's what we often do. We often do in science is you're looking. Some people want the data to conform to some pattern. They have some kind of pattern, already preconceived pattern. That's not usually the way science works. The science works is just by observing nature and then just modeling it, rather than having some preconceived pattern and then trying to make the data fit it. And so take a look at experiments 1 through 3. I'll give you a little bit of time. How much time do you think you need to figure out the pattern in the numbers? I'll tell you, there is a pattern in the numbers. How much time do you think you'll need to figure out the pattern? It's a puzzle. 5 minutes? More? Let me zoom. Yeah, it's not so easy sometimes to find patterns, right? I mean, it's not so obvious. Unless maybe if you're this person, do you know this person here? Maybe this person can look at the numbers and automatically see the pattern. Do you know this guy, Terrence Tao, professor at UCLA? He's supposed to have the highest IQ ever measured. This guy's was reading at 2 years old or something like that, and did all kinds of stuff. But anyway, he's giving a talk on Thursday. I think I have registered for this talk, but is anybody interested? It's live streamed Zoom. Professor at UCLA. I'll post a link if anybody's interested in it. But I mean, maybe he could see the numbers. I couldn't see the numbers. So you try different things. So what do you try? What you're looking for is not what you're looking for is a mathematical pattern. Because the most concise definition of anything would be a mathematical definition of that. If you want to boil it down. If you want to boil down the behavior of a gas, and what's the most concise definition of the behavior of a gas? It'd be the ideal gas law, at least of an ideal gas. Because then that simple compact equation, describes everything, PV equals nRT, right? at least the physical properties of it, or the van der Waals equation for real glass or whatever. So we tried different things. We tried different mathematical equations. So when we're looking for patterns, let me try this here. One of the patterns might be, maybe there's a ratio, you know. And so try, you know, something like this. We're going to try 0.0640 times 0.0320 divided by 0.0360 times 0.0680. And so we'll just take a ratio of the products to reactants and see if there's some kind of ratio, you know, or whatever you want to try. You just try different things. And so if we try this, let's see what we end up with. It's going to be 0.064 times 0.032 divided by 0.036 divided by 0.068. And it comes out to 0.836. You know? And so this is what we call the product to reactant ratio, 0.836. 6. All right, then we're going to see if there's a pattern in the ratios. You know, looking at a pattern in the raw numbers, this is called data reduction. Data reduction is we try to take all those raw numbers and reduce it into other things that are easier to visualize. And so I'm going to try the same here. I'm going to take the product to reactant ratio here. And see what I get. And so I'm going to go 0.064 times 0.084. And I'm multiplying. Maybe I should add it. But if I add it, this is going to add up to 0.1 over 0.1. And yeah, there's going to be a pattern. Or is it? I don't know what it's going to add. We could try it next. Divided by 0.032. Divided by 0.016. Why multiply? You know, it's just a guess. Did somebody do it? I did it. And I get 10.5. So is there a pattern in the product to reactant ratio there? It doesn't look like it. Some kind of reproducible mathematical pattern. Maybe there is. Maybe there's a series, you know, a series of numbers that changes. Maybe not. But it doesn't seem like it's working. Well, we'll just do the last one to see if we get anything. And so 0.1078 times 0.1039 divided by 0.0922 divided by 0.0961, 1.264. So in other words, on the first experiment, I end up with less product. You know, it's less than 1 product to reactant ratio. On the second one, I end up with a lot more product. It's here. And on this one, I end up with a little bit more product. And so how do I know how much product I'm going to get? What do you think the fourth one should be? What do you think the product to reactant ratio for the fourth one should be? Probably something completely different or something similar. Well, what is similar, you know? So that, I think, isn't going to work so well. And so I think this failed, basically. We didn't really see a pattern, you know, reproducible pattern. So what we can do is we can try, because of the coefficients here, this is a 2, we have twice as much copper. So what if we do this? We do 2 times 0.064 I'm going to drop the 0 just to save space, times 0.032, and we're just looking for raw pattern, 0.036. I'm going to do 2 times 0.06. I'm doing here 6432, 0.036, and 68. So we'll do 2 times 0.036 times 0.068. So all I'm trying here is I'm going to try to double the copper, right, and see if I get some kind of consistent pattern. And why am I multiplying? Well, I could try lots of different things. I'm just looking for mathematical. You know, if the graphs work, then it's easy. You know, because graphs, if let's say we get a straight line graph for everything and it looks the same, then that's it, y equals mx plus b. You know, that's our pattern. And so let's try this. But you know, if I do the 2 times, what's going to happen? Well, the 2 is going to cancel out and we end up with the same thing, right? So it's not going to change anything so far. Do you have any other suggestions?
Square it.
Yeah, okay. Let's try to square it. So we're going to try to square the copper. Why? Who knows why? You're just trying different things until something works out. Because if you understood the theory tells us why. You know, the theory gives us the fundamental description, but we're not going from a theoretical approach. We're going from a observational or empirical approach. When you do an empirical approach, you know, there's no theory to help guide you. And so theoretically, what does it mean to square it? Well, I don't know what it means theoretically to square it, but we'll just try it anyway because we're running out of options. 0.064 squared times 0.032. We're going to raise this to the first power because this is just coefficient of 1, divided by 0.036 squared and 0.068. And so if I square those, let's see what it comes out to here. So 0.064 squared times 0.032 divided by 0.036 squared divided by 0.068. 1.48. 7. We're allowed 4 sig figs. I didn't carry it. When we're allowed 4 sig figs, I'd like to write down 5. But the 5th one is not allowed. So usually I'll subscript it like this here. .487 sub 2. That means that extra digit there is not allowed. Here. All right, so let's see if there's a pattern that exists here. And so we're going to go to the next one. I should have done this a different color, but we'll try it again here. And so this is going to be 0.064 squared times 0.084 divided by 0.022 squared times 0.016. So let's go ahead and punch that in. 0.064 squared times 0.084 divided by 0.022 squared divided by 0.016. Oh, this is not 2,2, this is 3,2, sorry. I made a mistake. It's 32. Let me redo the calc. So unless somebody else has the calculation done. 0.064 squared times 0.084 divided by 0.032 squared divided by 0.016. Someone have it?
Mm-hmm.
21? So can we make a prediction what the next ratio should be? 42? Did you calculate it? Or are you predicting it? Predicting it? All right, let's test your prediction. 42. And so we'll try this. I'm going to not write out the equation. I'm just going to do this. 0.1078 squared times 0.1039 divided by 0.0922 squared divided by 0.0961. And the ratio comes out to not 40. What did you predict? 42. You know what the ratio comes out to? Oops. Did someone calculate it?
1.47.
Yeah. 1.4779. We're allowed 4 sig figs, so I'm going to carry this extra 9 like that. This comes from 0.1078 squared times 0.1039 divided by 0.0922 squared divided by 0.0961. And that gives me 1.4779. So let's take a look at the number. It didn't come out to 42, but take a look at the numbers here. Look at what did our first one come out to? 1.487. And our third one came out to 1.4779. So the 3 sig figs, the first one came out to 149, and the second one came out to 148. Are those pretty close? Those are pretty close. But our second one was way out there. Let me double check the second one's calculation. Maybe I made a mistake here. So double checking the second one's calculation, and let me make sure I got the data correct for the second one. $32, $16, $64, $84. Oh, no wonder. I screwed up the data for the second one, sorry. I didn't write it correctly. If you make a mistake, just exit out. Like I made a mistake there. I'm going to go back down to experiment 2. Two copper 2 plus a tin 2 plus yields 2 copper 1 plus a tin 4 plus. Initial was 0, 0, 0.100. 0.100. There's going to be some change. I don't know where I got those numbers. I could have gotten that number from something else. I was looking at the data here. This is the data from 2, so 0.0567. .0283. 0.0433. 0.0717. Again, oh shoot. I wrote these in the wrong spot. Let me fix that. Select these. This is not experiment 4's data. This is experiment 2's data. I'm not able to. Well, anyway. That belongs here. So let's see what the ratio is for this one. So this is going to be 0.0433 squared times 0.0717. The units cancel out, so that's why I'm not even bothering with the units here. Divided by 0.0567 squared divided by 0.0283 squared. And so let's see what this one comes out to. 0.0433 squared times 0.0717 divided by 0.0567 squared divided by 0.0283. And do you know what it comes out to? 1.4775. So do you see a pattern there? Yeah, the first one was about 148. $148, $149, let's say. The second one came out to 148, and the third one came out to 148. Is there a pattern there? It looks to be a pattern. It's not exactly the same because of experimental, of course, experimental errors, but it looks like it's like 148. If you average those, 2 at 148, 1 at 149. And so we're going to make a prediction for experiment 4. So I'm going to rewrite this one here. Two copper 2 plus a tin 2 plus yields 2 copper plus a tin 4 plus. And initially I'm going to have 0.100 moles of this, 0.050 moles of the tin, 0 moles of the copper plus 0.100 moles of the tin 4 plus. And there's going to be some change, and there's going to be an equilibrium state consisting of the amounts at the end of this reaction. So what we want to do is we want to predict it. And so what do we know mathematically? And so we're just going to try to figure out what this is. So why don't you use that ratio right now and tell me what the end concentrations are going to be. So this is what we want to determine here. We want to determine how much we're going to have of each of these 4 at the end. How are you going to determine this? Okay, how do you know it's minus 2x here? Well, we need to figure out what the change is going to be. So if we go back up here, Look at the first one. Yeah, it's a minus 2x minus x plus 2x plus x. And then we just figured out what x is, correct? That's one way. However, if we look at the second reaction was plus, actually, this is what it's going to be. The second reaction, let me finish this table here, 0.0567 moles. So in the second reaction, we started off with 0 moles, and we end up with 0.0567. So this has got to be plus 2x. Plus 2x is going to be plus 0.0567. If that's plus 2x, then plus x is half of that. What's half of 567? 283.5? So this is going to be plus 0.0283.5. And so this is going to be our plus x. And so we should end up with plus, we'll just round it to 283. And that's what's observed here. This is the stoichiometry. And this one will be minus 2x because we're going backwards here. And that's going to be minus 0.0567 moles. If we have minus 0.0567, then we're just going to be left with 0.0433 moles here. And this is going to be minus x, so that's going to be half of that. This is going to be minus 0.0283. And so we're going to end up with 0.0717 moles here. So how do we know if we go forward or backward? Because, you know, in the first case, it was minus 2x minus x plus 2x plus x. Why don't we use the same thing here? Well, the reason we don't use the same thing here is because we're starting off with 0. If you have nothing, do you have anything to lose? You have nothing to lose. We cannot go forward. And so the only way we can go from 0 is up. And therefore, if we have a 0 in there, it's always got to be plus there because it's impossible to go down, minus. Likewise up here on experiment 1 here, we're starting off with 0, so the only way we can go is up here, plus. However, in experiment 3, it's different. In experiment 3, how do I know which way I go? Because here I have both reactants and I have product. So do I go net forward or do I go net reverse? You know, when I only have reactants and I go forward, if I only have product, I go reverse, but now I have equal amounts of everything. And so which way do I go? Well, it just so happened I went forward, but can you say with certainty that all these are going to go forward? No, you can't say that with certainty. And so the only way I knew that this went forward is because I knew what happened here at the end. What happened at the end was I lost some reactant and I gained some product. And so that's something else we want to predict. We want to be able to predict these things. How are we going to predict it, which way it goes? Well, this one, experiment 4, we can predict. And you were right, Rebecca. It does go forward. And how do you know experiment 4 has to go forward? Experiment 4 must go forward because, yeah, I have 0 moles of copper plus. It can't go reverse because there's nothing to lose here. Right? The only way it can go is forward. And so I don't know what x is, but we want to figure out what x is because here we're going to have, we want to know. And it's not the percentage. If x were a percent, let's say it's 17%, then we could just go ahead and say, oh, well, we're going to lose 17%. It's going to be 0.017, right? But the percentage is not a reliable indicator. Do we see a pattern in the percentages? We did not see a pattern in the percentages. So this is going to be minus 2x, minus x, and this is a 0, so the only way we can go up is up. The only way we can go is up. And the tin 4, this is going to be plus x here. So now we're going to have to use some like Terence Tao style mathematics and figure out how we're going to figure out what x is. So we have one unknown, therefore we're going to need one equation. Do you have an equation? Well, I don't know, we kind of had two unknowns here because I want the copper 2 plus at the end. And that's going to equal 0.100 minus 2x. And so I don't know what this question mark is, and I don't know what x is. Therefore, can I solve this? No. So I have two unknowns. Now I have three unknowns because I have the tin. So I have a bunch of unknowns, but not enough equations. So I need more equations. Give me another equation. The other equation is going to be the pattern. If this pattern holds, then we call it a law. And if we call it a law, then we can just use the equations just like the ideal gas law to calculate it. And so what I'm going to do is I'm going to use this, and I'm going to try to call it, it appears to be constant. And so this is my law. I don't know if it's a law yet, but this is my proposed law. My proposed law is that the amount of copper plus here, so I'll just say that I'm going to have, whatever. This is all going to be different. So this is going to be x. Actually, I shouldn't call x. I'm going to use different ones. I'm going to say, I'm going to call this A. And I'm going to call this B. B is going to equal 0.050 moles minus x. And I'm going to call this G is equal to 0 plus 2x. 0 plus 2x is just 2x moles. The units here, moles. And I'm going to call this H. And this is going to be 0.100 plus x moles. And so what I'm going to do here is I'm going to just say G squared times H divided by A squared times B. Should be 148, That's what we round it to. Looks like we can round it to 148. All right, now I have way too many unknowns, and so I got to get rid of some unknowns here. I'm going to get rid of some unknowns by substitution. So I know what G is. G is 2x, and I'm going to square the whole thing. And then H is 0.100 plus x. And then A is 0.100 minus 2x squared. And B is 0.050 minus x. I want the moles on the outside. It's equal to 148. Now, I look at this, and are you guys good at algebra? You say? Sure. Yeah. This is going to be what order algebraic equation? It's like a third order. We could get it into forms. The calculators can solve this. My calculator can solve this. My calculator I'm using is the Casio FX115. You could solve third orders, except I have to get it into this cubic form. Ax cubed plus bx squared plus cx plus d equals 0. And so if I get it into cubic form, then my calculator can solve this. And that calculator is loud. You can do that. So my calculator solves both the quadratic and cubic equations. But I have to think, because if I multiply this out to get it into cubic form, is that going to be an easy thing or difficult? For me, it's difficult. You know, if I wrote this as 4 sig figs, it makes it even worse. You know, multiplying out all these numbers. And so I have to weigh things. One, if I get this into cubic form like this, then I can just plug it into my calculator and have my calculator solve it. That's one. But that's okay for quadratics and cubics. But what if you have a 4th order, a 5th order, or 6th order? Can you solve those easily? You know? And so let's say I had an ax to the 4th, or ax to the 6th. If I had an ax to the 6th, bx to the 5th, cx to the 4th, etc., can you solve that equation right now with the math you know for x? Do you want to solve it by hand? Some people said they'll just graph it. And so I'm going to weigh this, even though my calculator is allowed as a non-programmable calculator. It's a $20 calculator. This $20 calculator can solve quadratics and cubics like this. I'm not going to get this into quadratic form. This is a bit tough mathematically to solve. I'm not a math person. So what we do is we're going to try the method of successive approximations. In Appendix A. All right, so let's take a visit to the method of successive approximations in Appendix A of our book. Appendix A, for the most part, is math review. So if you need freshening up on any math, this is good. Scientific notation, using a calculator, addition and subtractions, multiplication, division, exponentials, logarithms. We're going to be using lots of logarithms this semester. Natural logs and log-based tens. So it might be good to review this. Quadratic. If you're a holdout and don't want to get the quadratic solver, then here's the quadratic equation. Go ahead and solve this. You got to get it in quadratic form. But we're going to look at this method, the method of successive approximations. We could solve the quadratic using this. Sometimes it's faster to solve it by this method than actually plugging it into the quadratic, especially when you have a lot of sig figs. And so I'll weigh that. If I have to do it by hand, then I might do anything by successive approximations because it just might be plain faster. A method of successive approximations is just a fancy name for the guess and check method. Have you heard the guess and check method? So this is going through an example of the method of successive approximations here. I don't do it exactly like they do it here, but it's just one page. Take a look at the method of successive approximations and read through that if you'd like. This is the method of successive approximations in a nutshell. You might be able to just take one guess to guess this, And so we'll do an example here. We can punch this in the calculator, or we can just go ahead and solve it in our head. Can you guess x in, guess a value for x? I'm going to guess x is equal to 2.5. So if I guess x is equal to 2.5, right, then I go 2x is equal to 2 times 2.5. That's equal to what? 5. Well, 5, it's not a match of 6. So that's my first guess was a failure. Okay, so this is my first guess. Let's go with my second guess. And your second guess might be different. My second guess is I'm going to guess x is 3.1. So I was too small here, so I got to guess x bigger. And so 2 times 3.1 is going to be 6.2, and I'm too big. So this is too small. This is too big. And then, okay, if that's too big, what do you think my third guess should be, maybe? My third guess is I'm going to guess that x is, well, I'm just a little bit too big. And over here I was way too small. So if I'm just a little bit too big, I'm going to guess that x is 3. If I guess x is 3, then 2x is 6, and then that checks out. This is the method of successive approximations. We just try to narrow down the guess until we get closer and closer. The problem is, what should your first guess be? You know, my first guess was 2.5. It's just, this was just kind of a random guess. It was kind of random guess. What if I guessed that x was 1 million, 50? You know, it depends. Then you're pretty far away. You might be guessing for a long time, Or you might guess that x is 3 on your first guess and get it. We're going to be constrained about our first guess, and here our first guess is going to be depending on different things. But could x be 0.1? X cannot be 0.1 because 2 times 0.1 would be negative 0.2. And if x were negative 0.2, then we have negative 0.100. Is it possible to have negative moles? No. And so x has to be equal to or smaller than 0.050, but it has to be greater than 0 here. And so that means our range for x is limited. It's between 0 and 0.05. And so what do you want to guess as your first x? I probably wouldn't guess 0.05. If I guess 0.05, then that means that all of this reacts. Or not all of it, but a lot of it. All the tin would react. Actually, I better not guess 0.05 because that would get this to 0, so that means all of it reacts. But we know this is partial reaction. And so what we're going to do is we're just going to guess an x. What do you think? Well, when we look at the ratio, it's 1.5, so we have a little bit more, it looks like a little bit more product than reactant. All these look like there's kind of a balance between product and reactant. So what we're going to do is we're just going to come up with some kind of guess between 0 and 0.05. And so going back to our problem, this is what we want. We want 1.48, which is the pattern that we saw, which is going to equal 0.100 minus 2x squared, 0.050 minus x, divided by 2x, 0 plus 2x squared, divided by 0.100 plus x. Oops, did I screw this up? I did. Sorry. This is the reactants over the products. We want products over the reactants. This is going to be 2x quantity squared. 0.100 plus x divided by 0.100 minus 2x squared divided by 0.050 minus x. Sometimes we simplify this. One of the things we can simplify this to save us a little bit of time is just go ahead and multiply this out. I'm just going to write this as 4x squared 0.100 plus x. Actually, this is not third order. What am I thinking? This is not a third order. What order is this? Oh, it is third order. X squared times x. This is third order. 0.100 minus 2x quantity squared 0.050 minus x. All right, give me a guess. Between 0 and 0.05. 0.03? Okay. Your first guess should only be 1 sig fig to save yourself punching so many numbers in your calculator. If you did your first guess as a 0.031258, you imagine punching that in the calculator all the time. It'd just become a pain. And so I'm just going to do 4 times 0.03 squared. 4 times 0.03 squared times, I'll do parentheses, 0.1 plus, actually I can just do that in my head, 0.13 divided by 0.1 minus 2x. 2x is going to be 0.06. So 0.1 minus 0.06 is 0.04 squared. So I'll just do divided by 0.04 squared divided by 0.05 minus 0.03 is just 0.02. So I'll just say divided by 0.02. And I get 14. 14.625. And what I'm looking for is 1.48, so I'm too big. Too big. And so what I'm going to do is I'm going to guess an x value that's, our target is 1.48. And so what's my next x guess? I'm sorry, x is equal to 0.02? 0.003? Like 10 times smaller? Okay, we'll try that. So I'll just go ahead and do it. It's going to be 4 times 0.003 squared. And then I'm going to do times, I'll put it in parentheses this time, 0.1 minus or plus 0.03. So it's going to be 0.103. I guess I don't really need parentheses. Are we out of time?
Yeah.
Yeah, all right. You can just finish this here.